So now we're going to apply the idea that we saw above, generating distributions of an estimated parameter, to actually create a statistical test. And with bootstrapping, the way you generate the distribution of your estimator is actually by using the sample that you have already observed. And the nice thing about bootstrapping is that it forces you to think in a constructive way about the sample that you have and how it was generated. And more importantly, how it would be generated under the null hypothesis. So to see how this works, we are going to create our own samples so that we fully understand what the underlying model is. And then we're going to create a test for the statistic that we observe. And the statistic will be the difference in mean between two samples. And then we're going to use bootstrapping to generate the distribution of that particular statistic. So basically what we're going to do is we're going to draw samples from two distributions, and we call the distributions A and B. So you can think of men and women, or people having observed different versions of a website, and we're interested in which website convinces people better to actually buy something. So let's say we're going to again generate a sample with size 50. Let me just switch on my completion. I'm deviating here a bit from what you see in the notebook. So just to make sure that you have both this, the video where I explain what's going on, but you can still use the notebook as well because it's not completely identical. So now we're going to say that A is equal to random draws from a normal distribution. So it's going to be sample size. We're going to have a mean equal to 10. And we're going to specify a standard deviation equal to 2. So this is how we draw the A sample. And for simplicity, we can actually copy what we have here. And we're going to divide the mean of the B sample by delta. Yeah, so actually I know by generating the data that on average B will be smaller than A. So now I can actually see what these things are, so I can print the mean of A, and I can print the mean of B, and moreover I can define the observed difference as being the difference between the mean of A and the mean of B. Yeah, so what we see in this case, so numbers will of course be different in your case because it's random, but for our sample the mean of the A sample is 10.4 and the mean of the B sample is 9.2. And the question that we have is this difference big? Or, to use the word in statistics, is this difference significant? Now instead of jumping to your statistics book to find a test on comparing two sample means, let us simply think for a second. So our null hypothesis would be in this case that, let's say, A and B have been drawn from the same distribution. So one way I can actually implement that using the samples A and B that we have is to say that the samples have been drawn from the combination of A and B. So let me be a bit more specific. So I'm going to define a new data set called AB, which is the combination, so the concatenation of A and B, B along the 0 axis, so along the rows. To make sure that it's easy to read these things, I'll turn them into numpys. And then I can ask what the shape is. Yeah, so now AB is simply a data set with 100 rows. So I've taken 50 observations for A. So that's a vector, and I have a vector of 50 observations of B, and I glue them together, one column vector below the other one. Now, according to our null hypothesis that A and B have been drawn from the same distribution, I can now draw my samples out of this combined data set AB. And we're going to do that 10,000 times. So I'm going to generate 10,000 differences between the mean of A and B. And I'm going to see whether these generated differences are as big as the observed difference that we have in our data here. So I start with an empty list called differences. And now what I'm going to do is for I in range 10,000, so I'm going to do this 10,000 times. I'm going to shuffle the dataset AB. Yeah, so that means that after I've shuffled it, what was previously row 20 is now row 80, and what was previously row 100 might now be row 10, etc. So all the rows have been shuffled. So in particular, the A and the B observations that we had out of our samples A and sample B have now been mixed together. So we don't know exactly what's A and what's B anymore. So now I'm going to append to our list of differences a new difference, which I'm going to define as follows. So let me first type it and I'll explain what it is. So I'm going to take the mean of my new A sample, which I define as minus the NP mean see how the brackets are going here. We need another one. No, so that should be it. Let me see. Yeah, so that runs without an error. So what I've done is, so each time I go through this loop, and I go through this loop 10,000 times, I first shuffle the data set AB, which has 100 rows. So each time I go through it, I get a new order of the observations that we had in our original samples. And then I say my original A sample is basically the first 50 observations in AB, and my observed B sample are the last 50 observations in AB. So each time I shuffle, these will be different. So the way that works is that because I have the colon here and then 50, this basically means for Python to take the first 50 rows out of AB. And here I first have the 50 and then the colon, so then I'll take the last 50 observations out of AB. Of course, the way I identify A and B here is completely arbitrary. I could have switched these two around, because under the null hypothesis, they're drawn from the same distribution. So we're drawing everything from the same distribution, so it doesn't really matter how I identify the A sample and the B sample. Yeah, so I could have identified the A sample as all the even rows in AB, and the B sample would be all the odd rows in AB. Or I could have defined the A sample as going from index 50 all the way to the end, and then the B sample would start at index 0 and go all the way up to 50. Yeah, so that's actually completely arbitrary. So now the important thing that we want to know is, how likely is it that the differences that we found, so we have differences that are bigger than the observed difference that we defined above. Yes, so that's what we defined here. Here we have the observed difference being the difference between the mean of A and the mean of B. So here I'm generating again a list of booleans, which are a combination of trues and false. The trues are represented in Python as ones, and the false are represented as zeros. So when I sum, I get the number of times that the difference is bigger than the observed difference that we had seen ourselves. And to turn this into a probability or a frequency, I'm going to divide this by the length of differences. And the result is 0.0016. Yeah, so under the null hypothesis that A and B were drawn from the same distribution, it is actually highly unlikely that I find a difference which is equal to our observed difference or even bigger. Yeah, so the conclusion is that actually the difference between A and B is significant, and we reject the null hypothesis because it's actually so unlikely given the observed difference that we saw in our original samples, that we decide that A and B were not drawn from the same distribution.